Well, thank you very much. I want to thank you all again for bearing with me for, well, it was planned to be 4, but actually 5 lectures for me. So that's a lot of Andy Putman, and I'm really sorry for that. But, this is the last one. It'll be over. So let me recall a definition from last time. Recall, so a coherent sequence of SP Z reps over a field F is, well, we have a sequence V1 connected by a map to V2, connected by a map F2 to V3, connected by a map F3, so on, such that 2 things hold. I'm stating this a little differently than last time. So V sub G is a SP2G Z rep over F. And so now F sub, let's say F sub G, that's going from, well, I'm going to say it's F, it's going from VG minus 1, but now I'm going to take an external tensor product with the trivial representation going to V sub G is SP2 times G minus 1 Z cross SP2 of Z equivariant. And so this encapsulates the definition I gave last time. Here, we're embedding this inside SP2G of Z in the natural way. Okay, so this is the definition I gave last time. Here I'm sort of, I had the condition that SP2 acted trivially, and that's how I'm stating it differently here. I'm using, this is, an external tensor product. That's we have a representation of SP2G minus 1, and that's the trivial representation of SP2, and so it sort of is a different way of stating that definition from last time. So this is the definition, and the theorem that I want to discuss at the beginning of today is the stability theorem. Which is, this is due to Minahan and myself. So, which says the following. So V1, F1 to V2, F2 to V3, so on. So be a coherent sequence of SP Z reps. What did I do wrong? Wait, can you say it louder? The end, did I? What is this? Indices. V1 goes to F1. Oh, you're right. Yes, that's F. There we go. Now is everyone, okay, good. Getting things like not off by 1 and getting all the signs right. You're not going to get me to do that in public, okay? I apologize. If you have a product of 2 groups, right? So you have, yeah, as a vector space, this is just the tensor product. So it's the same vector space as VG minus 1. I'm tensoring with the ground field, right? But now I'm telling you, yeah. So this right here, VG minus 1 is a representation of SP2G minus 1, right? The trivial representation is a representation of SP2, and their tensor product is a representation of their product. I don't know. It's a representation theory convention. So, yeah, I don't know why. Not every representation theorist does this, but a certain percentage of representation theorists use the box to denote when you're trying to take the if you have a product of 2 groups and a representation of each, you want a representation of the product. So anyway, over a field, so F of characteristic 0, so assume first the first condition is that the co-kernel, assume that for g greater than or equal to g naught, first the co-kernel of f g minus 1 is a finite dimensional algebraic representation of SP to g minus 1 of z. It's actually a representation of SP. It's a representation of this product, but I'm saying nothing about the second factor. Okay? It's a finite dimensional algebraic representation of that, and also that the co-invariants, so that go from it's v sub g sp 2gz. So we're taking the largest quotient of vg on which sp2g acts trivially, so our finite dimensional. And so the conclusion then is that v sub g is finite dimensional for g at least g naught, and algebraic for g greater to g naught plus 1. Okay, so this is the stability theorem I stated at the end of last time. So are there any questions about this? Hopefully I've gotten the indices correct this time. So I'm not going to prove the representation theory part, but I'm going to prove, so here is the proof of finite dimensionality. So which is quite short. And this will not, and the proof of finite dimensionality does not use the fact that we're working over a field of characteristics 0. That comes in because I only understand the representation theory of the symplectic group over a field of characteristics 0. So that's where, so the fact that f could be z in what I'm about to do right here. It doesn't really matter. But this shows up when we're trying to deal with the algebraicity part. So how does this work? Well, let me introduce some notation. So we have that, so let's let G be 1 cross SP2 of Z. Oh, let's consider, of course, some G that's greater than G naught. Let's let this be that's a subgroup of SP2G of Z, and let's let W, that's the image of f g minus 1. That's, of course, contained inside Vg. And so thus, so G, it acts on W trivially by the way I set things up, right? That's by the definition of a coherent sequence. So now I want to make an observation. So for M inside SP2GZ, of course, if we conjugate G, so we look at M, G, M inverse, this acts trivially on M times W, right? Because that's, that's how conjugation works. We're sort of like changing our basis, changing where these things go. And so now comes what we observe is that, so SP2G of Z is normally generated by G, right? So it's generated by conjugates of G. Just because, for instance, this SP2 contains a symplectic transvection, right? It's one of them. And as you conjugate all the symplectic transvections, you get things that generate SP2G of Z, right? Because that gives you all the symplectic transvections. So we can find, so M1 through Mn inside SP2G of Z such that SP2G of Z is generated by the union, as I goes from 1 to n, of the conjugate M sub I G, M sub I inverse, okay? So the symplectic group is generated by the conjugates of G, and it's finitely generated, so you just choose an appropriate finite set of conjugates, just quite large. It doesn't really matter how big it is. such that you're generated by the union of those conjugates. Okay? And now let's set so U to be the intersection, as I goes from 1 to n, of m sub I times W. What do I know about U? I know two things. Then, first, so we have that each, so m sub I g m sub I inverse, acts trivially on U. So in fact, the whole group sp2gz acts trivially on U, right? Because we've shown that a generating set for the symplectic group acts trivially on U, okay? Because we know that this conjugate acts trivially on this, and we're intersecting all those, right? So we're intersecting, this thing is small enough so that all those things act trivially. But we also know something else. We also know that, so since the co-kernel of f g minus 1 is finite dimensional, so W inside Vg has finite codimension, right? So thus, so does, so its orbit, m sub I W, and hence U inside Vg has finite codimension. Because I'm intersecting finitely many subspaces, each of which has finite codimension. So the codimension can't become infinite. Okay? So I have these two properties. I found this subspace which has finite codimension on which the symplectic group is acting trivially. Are there any questions? This is the sort of key. We're almost done. So what happens now? Well, i.e., we have a short exact sequence. 0 goes to U, goes to Vg, goes to Vg mod U, goes to 0, where, so what we want to show is that Vg has finite dimension, right? We want to show Vg is finite dimensional, and we know that this right here is finite dimensional, right? And we also know that this right here is a trivial, so sp2g of z rep, right? So we have a short exact sequence of representations. This right here is trivial. This right here is finite dimensional. So we want to show, to show that the dimension of Vg is less than infinity, it's enough to show that the dimension of U is less than infinity, right? But now we have a short exact sequence of representations of the symplectic group. We can, if you have a short exact sequence of representations of a group, you get a long exact sequence in group homology. So associated, so to that is a long exact sequence in sp2gz homology, which contains, well, here we're going to have H1 of the symplectic group with coefficients in Vg mod U. That goes to H0 of the symplectic group with coefficients in U, that goes to H0 of the symplectic group with coefficients in VG, and then I could go to H0 with coefficients in VG mod U, but I don't need that. Okay? Now what do I know? Well, this right here, this is finite dimensional, right? Because sp2gz is finitely generated, and this is a finite dimensional representation, right? So homology will be finite dimensional. This right here, well, what is H0? H0 of a group acting on a vector space is the coinvariance. In fact, that's one definition of group homology. Group homology are the derived functors of the coinvariant functor. They're the correction to the fact that taking coinvariance is not right exact. Okay? That's a very good definition of group homology. The same way that Tor is like, you know, the derived functors of the tensor product. Okay? So this right here is U sp2gz, and this right here is VG sp2gz. That's what H0 is. Well, this right here is also called U because the symplectic group is acting trivially, right? And this right here is finite dimensional by assumption. That's one of my assumptions. That's assumption 2, right? And so thus, we conclude, oh, and this right here is, since, you know, this is the trivial action. So, you know, groups acting trivially, we kill off the action, nothing happens, right? And so we conclude that that U is finite dimensional, which is exactly what we had to show. I find this a very mysterious proof. It's not that hard, but like somehow, like to my mind, the assumptions feel too weak for this to work, but they do actually work. Yes? Right. It works if f could be the integers. For this part of the proof, I don't need that. That shows up when you want to prove algebraicity. Yeah. Yes? No, because invariance and co-invariance, well, so if I did that, let me look at this thing, right? Let's look at the proof right here. So I could do, so if I did that, then I get the arrows going the other direction. Yeah, I mean, I guess I could also say that the invariants are finite dimensional. I just use cohomology instead of homology. Either way, this is sort of my bias. So like I am a very strange kind of algebraic topologist. Like I think homology is better than cohomology, even though like at a spiritual level, that's not a true statement. You know, cup products are better than whatever homology has. So, but I just sort of prefer homology. So, any other questions? It would that's you know, in some sense like so the co-invariants are the invariants of the dual, and so in some sense that like what that means is that it's, you know, in some you're going to end up proving the same sorts of statements one way or the other, whichever one you use. Okay. So are there any other questions about this proof? Yes. Yeah, so I know that this is finite dimensional, right? And I know that this is a finitely generated group. If you have a finitely generated group acting on a finite dimensional vector space, H1 is finite dimensional. Yes? Right, yeah. That's right, exactly. Yeah. Taking covariance is not, it doesn't preserve injections. That's right, yeah. That's why you need this. Yeah. That's right, yeah. Exactly, yeah. Like the reason that group homology exists is because the covariant functor does not preserve injections. Almost nothing. Like almost not, like, and it's generated by like conjugates of this sp2. Right? Those are the two things I'm using. So I should say, like, this part doesn't really show you where the symplectic group comes in. The algebraicity is where you start using the fact that this is a lattice in a more serious way, because you really need to know things about the representation theory of these groups. So, and it works for other lattices too. It works for SLNZ or SLN of a number ring. You can prove this, similar kinds of statements. But you know, I'm stating things for the symplectic group because that's the group that's relevant for the Torelli group, and somehow, you know, I'm a believer in stating like the simplest possible case of things I'm using rather than trying to state general things, because I'm not very smart and I can't keep track of general statements. So, any other questions? I said last time this would take me 20 minutes, and look at that. It took me exactly 20 minutes to prove this. So anyway, what is my goal now, if there aren't any further questions? So my goal is to use this. So my goal now, so in my paper with Dan Minahan, we use this to prove that H2 of the Torelli group is a finite dimensional algebraic representation of the symplectic group for G at least 6. That's quite, the verification of that is quite difficult. But if I go down to H1, things become much easier. So my goal is to apply this to show that H1 of Torelli G1 with Q coefficients is finite dimensional for G at least 3 and algebraic for G at least 4. It's actually algebraic for G is equal to 3 as well. And if you stare at this proof and what the sort of things that go into it, you can see that. And if you stare at the proof even more, you can actually see what representation has to be, because we're actually gonna not just show the hypotheses, we're gonna literally calculate both things here. We're gonna calculate the co-invariance, and we're gonna calculate the co-kernel. Okay, and once you know that, it's not, you know, going from there to the actual calculation is not particularly difficult. But this is the easiest example of how to do this, and the sort of the basic idea, the sort of space I'm gonna construct to prove this is exactly the one we use to understand H2 of Torelli. So this is what I want to do. So now there is one statement. So there's sort of two things that I need to verify, right? So I need to verify the co-invariant statement and the co-kernel statement. And so let me give you a little exercise. So there's going to be, because I find it very hard, like personally, I find it very hard to lecture about detailed calculations. And I also find it very hard to listen to someone lecture about detailed calculations. So I'm going to tell you how to do a few calculations and what the answers are, and let you do the calculations, okay? So here's one calculation. So the Serre spectral sequence, or I guess it's the Hochschild-Serre spectral sequence. Sequence for 1 goes to Torelli G1, goes to mod G1, goes to the symplectic group. Prove that, well, in fact, for, I guess, that for all G, so we have that if we take H1 of Torelli G1, I could put Q here. I'm not even going to put Q here. It works over Z. You take the SP2GZ co-invariance, which, by the way, remember, from, as I said before, that's H0 of SP2GZ with coefficients in H1 of Torelli G1. So which of course is a term in that spectral sequence. This is in the E2 page, is finitely generated. So hint. So all homology groups of mod and sp2g of z are finitely generated. So that, like there, and then you just look at the spectral sequence and it's going to pop right out at you. That sound is a technical term. Like it sort of shows you it really does make that noise as it comes out of the spectral sequence. Okay? So, i.e., the co-invariant statement is very easy. The co-invariant statement is sort of formal. So, the co-invariant statements. What do you say? The homology of the mapping class group is finitely generated. Yeah. So the the co-kernel statement is easier to prove over Q, but the co-invariant statement is just very formal. It works over any field. It works over T. So the co-invariance, statement we need is easy, and we must prove that the co-kernel of the map from H1 of Torelli G minus 1, 1, and I'll put with Q coefficients here. You could soup up what I'm going to do to work here over Z, but I'm not going to. It is easier over Q. To H1 of Torelli G1 with Q coefficients. So must prove that is finite dimensional algebraic rep of sp2 G minus 1Z for G at least 3. And somehow like this isn't going to be true for G is equal to 2. So you have to use G at least 3 somewhere to make this true. The co-invariant statement works for all genus. It's very soft. So this is what I'm going to spend the rest of today's lecture showing, is this co-kernel statement. And how am I going to do that? I'm going to define a space. So here is, let's see, I need a blue piece of chalk and a red piece of chalk to define the space. So here is what I'm going to do. I guess I can make some definitions here. So here's so alpha and beta be the following. So I'm going to draw myself a picture of my surface. This is my genus G surface. Nice and big. It's got a genus at least 3, so I drew the minimum genus 1. And so I'm going to first choose 2 points here. We'll call that x0, and that point is x1. There are 2 points in the boundary, and so I have this arc right there. That's an oriented arc connecting x0 to x1. I'm going to call that alpha. And then I'm going to have 2 points right here. There is y0 and there is y1, and I'm going to draw a blue arc connecting y0 to y1, and I'm going to call that one beta. You see, A is all out, so A is like the color apple, so it's always red, and B is the first letter of blue. So that's how I remember. I'm going to draw a bunch of red curves and blue curves at various points, and that's how I remember which one is which. Okay, and so here's some definitions. So definition. So I'm going to be looking at spaces of arcs connecting points in the boundary, and I want to fix the homology class of these arcs. And when I say the homology class of an arc, I mean in relative homology, right? Like I'm looking at an arc connecting 2 points in the boundary. That gives you a point in homology relative to the 2 points that are the endpoints. And so here's the definition. So an A arc is an arc alpha prime, in sigma G1 connecting, so x0 to x1 that is homologous to alpha in the relative homology group H1 of sigma G1 relative to the points x0 and x1, okay? That's a thing I can talk about, right? And similarly, define, so a B arc, similarly, using beta, okay? So I have a notion of alpha arcs and beta arcs. By the way, why do I call these alpha and beta? So I could close these things up to simple closed curves by just like, you know, instead I could just take this beta and just move those to there, and take this alpha and just move those over to here, and then I'll get curves alpha and beta that intersect once, right? So there's somehow like that, these sort of correspond to sort of an A1 and a B1 in a homology basis, but it's a little more convenient to take arcs rather than loops. Okay, so these are the two things I'm going to care about. And so now let me define a space for y'all. Well, it's not going to be a very complicated space. It's just going to be a graph, okay? So of course, there are many alpha arcs, and there's many A arcs, and there's many B arcs, okay? It's not hard to draw curves that are homologous, arcs that are homologous to these arcs that kind of go all over the surface. And so we can sort of try to collect them all into spaces. By the way, arcs, you know, all arcs are up to isotopy. Everything is defined up to isotopy, because I want the mapping class group to act in it, or the Torelli group to act in it. So definition, I'm going to call this H a B of sigma G1 be the graph with, I have to tell you the vertices and the edges, right? The vertices equal isotopy classes of alpha arc, of A arcs, and B arcs. Okay? I have two, so the vertices come in two flavors. There's the red vertices and the blue vertices, okay? And where the edges, we have an edge, so the edges, well, we're only going to have edges connecting an alpha arc and a beta arc. So we have an edge, so we connect, you know, so we have an edge connecting, so an A arc to a B arc, so when they are disjoint. Should remind you of a curve complex type object if you've seen that before. So we have, you know, we don't connect any two A arcs. Like those are always set, those are never connected by an edge. We only connect an A arc to a B arc, and we connect them if they're disjoint. Okay? This is a variant on a space I defined many years ago to find generators for the Torelli group. So it's maybe, you know, it's like a variant for surfaces with boundary of something that I defined a long time ago. And you can prove the same way. So this is a theorem so I'm going to attribute this, the paper, so this is a theorem which I'm going to attribute, well, I'll put myself there, but I'm also going to put Hatcher and Margalit. Is that this space HAB of sigma G1, it's a graph, is connected for G at least 3. Okay, so now Hatcher Margalit did not, of course, prove this because I just defined, as far as I know, I've never written this definition down in public. So what really happened was that I introduced a space, like a sort of version of this space for not arcs but loops a long time ago to find generators for Torelli, and I proved it was connected for G at least 3. But I used Johnson's explicit finite generating set for the Torelli group to prove that. Okay, and later on, Hatcher-Margalit gave an a priori proof, which sort of made this independent of our knowledge of the finite generation of Torelli. And they didn't prove this, but you do the same argument proves either one. Like you can prove that this graph is connected the same way you proved that the one that they dealt with is connected. Okay, so this is where we use G as at least 3. This is definitely not connected for G is equal to 2. So you can prove that. So if this was connected for G is equal to 2, you could prove that H1 of Torelli 2 was finite dimensional, which it's not. So in any case, though, so we have a graph, and now you see why I want G to be at least 3, right? Because that way I can have this graph be connected. So now comes another exercise. This is so I want to observe that the Torelli group acts on this edge, on this graph, right? Because the mapping class group takes isotopy classes of arcs to isotopy of classes of arcs, and it preserves disjointness. And the Torelli group preserves homology classes. Okay, so this is acted upon by the Torelli group. So here is an exercise. Oh, but there's actually more. Before I state the exercise, let me make an observation. So the Torelli group, it acts on this space, this graph AB. It acts transitively on the A arcs and the B arcs. That's basically due to Johnson. He proved something equivalent to that. And also transitively on the edges. And so i.e., the quotient of HAB by Torelli G1 is equal to a single edge, where you might as well label that with an A and that with a B. This is the orbit of the A arcs, and B is the orbit of the B arcs. Okay, so this is a very nice space. The quotient is it's a graph. Torelli is acting on it. It's connected. The quotient is a single edge. Okay, so now comes the exercise. So let's let G be a group acting on a connected graph X such that X mod G is equal to a single edge. Just like in our situation right there, right? So then, so E be any edge of X with endpoints. We'll call them Z0 and Z1. So the conclusion then is that G is generated by the stabilizers. So G sub Z0 union G sub Z1. So there are many results of this flavor in geometric group theory. You have a group acting on a space that's nice enough. You can find generators sort of by studying the action. In this case, like I'll tell you the sort of picture you should have in your head in words, right? You have an element of the group. You want to write it as a union of these stabilizers, right? You choose some base point, say Z0, and Z0 goes to some other thing way over here, and you can connect them by a path of edges, and then you just start taking your edge and you start swinging it around like this with using stabilizers to connect one to the other. Okay? So it's something like that. This is an extremely fun exercise. It's very, and it's elementary. Definitely use the fact that the graph is connected. Okay, but it's a variant. I mean, you know, since the days of Poincaré studying Fuchsian groups, we've sort of known how to find generators and relations for groups acting on sufficiently nice simplicial complexes. It's like a constant theme. Okay. If this was, by the way, if X was a tree, this would be immediate from Bass-Serre theory, right? In fact, if X was a tree, this would be like the amalgamated free product of this and this amalgamated over the stabilizer of the edge. So this is like a baby generalization of that. In any case, though, what do we see from this? Well, I have an edge of my graph right up there, right? So letting, you know, apply to the action of Torelli G1 on this graph, HAB, and the edge, so alpha beta as above, and we conclude that Torelli G1 is generated by the stabilizer of alpha union, I'll just write this right here, union the stabilizer of beta. Okay? Now, by the way, what do I do for H2? I think it's worth saying, you know, so this graph is not good for computing H2. This graph is connected. To compute generators for H2, it turns out I need something that's like 1 connected instead of 0 connected. And so I have to add a bunch of cells to these things. But we add the cells very carefully to make sure the quotient, well, it's no longer a single edge. The quotient's actually quite complicated, but the quotient will still be contractible. So like for computing generators for H2, you need the space to be 1 connected or at least 1 acyclic, and the quotient to be contractible. That makes then I can get things that are related to generators for H2. But that requires a more sophisticated complex than the one I wrote down. I need higher dimensional cells to make that work. So, okay. Let me state this. This is generated by 2 things. So in other words, so I thus have, let me summarize this. I'll write this on this board right over here. I have a commutative diagram that looks like the following. So I have a commutative diagram. Well, I want to make an observation that, let me draw this. I will draw this right here. Just I want to redraw it so I can, but I'm going to add one feature to this graph. Where did I put my red and my? I had a piece of red and blue chalk. I was holding on to them for a long time until I needed them again, and I had set them down. Okay, so I've got my alpha. Let me move this a little bit to the left. I've got there is alpha right there. And there is beta right there. And I want to make an observation that over here, disjoint from both of them is sigma G minus 1, 1, right? And so these stabilizers they contain G minus 1, 1, Torelli ingenious G minus 1, right? And so now, remember my goal, what I want to prove is I want to prove that the co-kernel of the map from Torelli G minus 1, 1 to Torelli G1, I want to show that that's a finite dimensional algebraic representation, right? And so I have a commutative diagram, that goes like this. Well, I'm going to give myself some space to write things down. I have H1 here, of Torelli G minus 1, 1. So now I'm going to put a little assumption here so I can stop writing it. All coefficients, all homology have Q coefficients. Okay, so I have that homology group right there, and I want to prove that this map over to here to H1 of Torelli G1. I want to prove that this map is well, it has a small co-kernel. It's like surjective up to something finite dimensional and algebraic, right? Maybe not surjective, but the co-kernel is very small. Well, in the middle here, I have H1 of the stabilizer of alpha plus H1 of the stabilizer of beta, and that map is surjective, right? And I have something like that. This is included in both terms here, right? Their intersection contains H1, it contains this thing. And so what do we see? What we see then is letting, so gamma be either alpha or beta, it's enough to show that the co-kernel of the map from Torelli H1 of Torelli G minus 1, 1 to H1 of Torelli G1 stabilizing gamma is finite dimensional algebraic. Okay? Because I'm killing off the image of it. Like in taking the co-kernel, I'm killing off the image of this, right? That kills off the same image in both of these, right? Because they're the same. And so I just have to show that what's left is finite dimensional algebraic, and there's a piece from this and a piece from this, and I have to show that they both work. Okay? Why is this arrow surjective? Because the group is generated by those two subgroups. Remember, H1 is like the abelianization, right? Right? Yeah. Make sense? Yeah. Any other questions? Really, it's like the free product of those two things surjects onto the group, right? But then when I take H1, the free product turns into a direct sum. So let me show you how to do this. In fact, let's calculate it. By the way, here's a little exercise for you. What should it be if I believe that H1 is given by the Johnson homomorphism, for the Johnson homomorphism junkies in the audience, the real sickos? You think that the answer should, the abelianization is supposed to be wedge 3 of H, right? The co-kernel, well, we're killing off like wedge 3 of H, but in one genus lower, right? What should be left? Things of the form alpha 1, wedge 2, and beta 1, wedge 2, right? So, and that's what these stabilizers should have. Like, so these things right here, I want this co-kernel to actually be wedge 2 of whatever the thing is supposed to be. That's what I expect. And that's what I will prove. So, I what? I will. Well, I'll sort of prove. I will state what you need to do, and then I'll leave it as an exercise, having given you all the ideas. So let's do it just for concreteness. Let's do it with alpha. Okay, so for concreteness, we'll do gamma is equal to this arc alpha. So what does the stabilizer look like, right? Well, I want to make an observation. So the stabilizer of, so if we look at the mapping class groups, so the mapping class group stabilizer of the arc alpha is supported on, the complement of a regular neighborhood, of alpha union the boundary of sigma G1. Let me show you what I mean. So here it is. Here's my surface. I'm going to draw it nice and big. Here is, there's genus 1, 2, and 3. Here is alpha right here. And so if I'm going to fix, so I know I fix the boundary, right? Because that's mapping classes always fix the boundary. If I also fix this, like what I'm really doing is I might as well fix a little neighborhood. So that neighborhood looks sort of like this. So in other words, we're supported here. Okay? So in other words, the stabilizer is contained inside something that's like genus G-1, but with 2 boundary components. So, i.e., the mapping class group 1 stabilizer of alpha is actually equal to mod G-1, 2, or is isomorphic to it. But it's supported over here, right? On this copy of genus G-1 with 2 boundary components, right? So if I have a mapping class that's supported here, it stabilizes alpha. And conversely, if it stabilizes alpha, I can homotope it to be the identity on this part right here, and that's basically canonical. So, okay? Isn't that neat? So I've sort of gotten myself down to genus G-1, but at the cost of having a boundary component. And so here's a thing that if you know the Berman exact sequence, or some version of it, gives something like the following. We have mod G-1, 2. Well, there's a map that goes to mod G-1, 1. And what is that map? That map looks like this. This map right here glues a disk to that boundary component right there. If we glue a disk to that boundary component, it becomes something with 2 boundary components. And this, of course, that's a surjection. And it splits like that by including this into that subsurface right there. Okay? And the kernel are things, what do? They take this disk right there that I glued on, and they allow it to move around the surface, and I can rotate and stuff like that. So I have to keep track of how this disk, like if the surface is made of rubber, it like moves around the surface, it rotates, and so on. And so this is pi 1 of the unit tangent bundle of sigma G-1, 1. Where this is like the disk pushing subgroup. Okay, so I have something like this. Maybe a better way of writing this thing is that I have a semi-direct product decomposition. i.e., so I have a split exact sequence, and that really says that mod G-1, 2 is the semi-direct product of pi 1 of this unit tangent bundle subgroup, semi-direct with mod G-1, 1, right? So split short exact sequences are the same thing as semi-direct product decompositions. Okay, so now here is a theorem. How does this restrict to this stabilizer? I'm taking a semi-direct product decomposition, but I'm now restricting it to this stabilizer. I have inside here, I've got this stabilizer of alpha. Okay, that lies in there somehow. And there's a theorem. This is, I proved this many, many, many years ago. This is when I was a graduate student. No, this right here? No, that's a genus G, because you may see I'm taking the whole genus G thing and I'm fixing alpha, right? Yeah. So because I'm taking something on genus G, but then I'm fixing this arc, that means I'm really living on this genus G-1 surface with two boundary components. And so I proved this many, many years ago when I was a graduate student. It says the following. So it says that let's let pi equal pi1 of sigma G-1, 1. So we have a similar semi-direct product decomposition. If we take the stabilizer, it says I reached my exercise goal while lecturing right now for the day. My watch just told me. So of alpha, this turns out to be, well, it's a subgroup of pi1, and it turns out to be the commutator subgroup of the group. Now this, you should be a little fishy because, well, this is like this, and there's no unit tangent bundle, but this is how it actually fits in there. This is embedded in here in a sort of complicated way. Semi-direct with Torelli G-1, 1. Okay? So you should expect like this thing right here, you want to look at things that fix homology, right? And so that's why you expect the commutator subgroup to show up. Like those are things that are, like if you look at how this acts on homology of the whole big surface right here, well, if you look at the an arc that goes like, a loop that goes like this, it's sort of adding something to that. That's what this disk pushing subgroup is doing. And so you want to add something at 0 in homology. That's why the commutator subgroup comes in. But now comes the following. So how do you abelianize a semi-direct product decomposition? Well, it becomes something very simple. So this implies that H1 of, so Torelli G1 alpha with Q coefficients is equal to the direct sum. We're going to take H1 of the commutator. So, but remember, I'm working homology as Q coefficients here. So that's part of I'm continuing to use that. And then we're going to take the co-invariance, because we have a semi-direct product decomposition. So there's an action of this on this, and we have to kill that. When we abelianize, that action becomes trivial. So we have to kill off that action. And so we get something like G-1, 1 there, plus H1 of Torelli G-1, 1. Right? Now, of course, the co-kernel is staring at us. So thus, the co-kernel of the map from H1 of Torelli G-1, 1 to H1 of the stabilizer is exactly isomorphic to those co-invariants, H1 of the commutator subgroup, and we kill off the action of the Torelli group. Okay, now, as I said, the real sickos know that I'm trying to prove this is wedge 2. And they also know that if you take the commutator subgroup of a free group, there's a natural map to wedge 2, right? You just kill out the next term of the lower central series. And so that's the exercise. It's not quite true that the Torelli group can perform any inner automorphism on this. It can come very close. But because we're using Q coefficients, like the problems that occur are really two torsion problems. And so here is the exercise. Exercise says that if we take H1 of pi, and we kill off the Torelli G-1, 1 action, that right there is isomorphic to wedge 2 of H, where H here, of course, is H1 of sigma Q coefficients, and the map takes the commutator. So we'll say, you know, I don't know, X, Y inside the commutator subgroup to something like X bar wedge Y bar inside wedge 2 of H. So if you've ever seen, you know, taking, you know, this thing right here, by the way, that's the same thing as pi pi modulo pi pi comma pi, tensored with Q, of course. So that's what that is. That's why you get a wedge 2 there, is because you get this commutator subgroup. And so this, if you've ever constructed the Johnson homomorphism, this is a move you should expect. You should expect exactly this term to be showing up somewhere, and it shows up right here. And that proves it. That's an algebraic representation. We're done. Thank you.